Hello and welcome to section 6.7. So over this and next section we're going to look at some applications of exponential and logarithmic functions. So in this section we're going to look at financial models. Alright, so there's a couple of formulas that we use in this section. The first couple of ones and the most important are the compound interest formulas. So this first one, A equals P, parentheses 1 plus R over N to the power NT. This refers to investing or spending an amount of money, which is P. So P is called the principal amount. This is basically the money that you're investing or borrowing, so this formula works in both ways. A is the amount of money at a particular time after you borrow or invest. So this is money at time T. We have R is annual interest rate. Interest rate in decimal form. Alright, so usually it's given in percentage form and you want to change it to decimals. N is how many times per year your interest is compounded. So number of times per year that the interest is compounded. Interest is, and that means just applied to the sum. And T is how many years. Yeah, so how many years your investment or your loan is occurring over. Okay. Now the second formula, continuous compounding, is when the interest is applied continuously. All right. So basically, every second, every millisecond. So the formula is this. So the amount in the account or that you own on the loan at any time T is equal to the principal, which is the original amount that you invested or borrowed, base E, so that base is that number 2.71 blah 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 that you find in your calculator, and RT, R is the interest rate in decimals and T is the amount of time in years. Okay, so with these formulas you're able to find the amount of money that you will have in the account or that you will own on a loan a few years down the line. Okay. So let's look at some examples for applying these formulas. So we want to find the amount that results after each investment. So I invested $50, so this is your P value at 6%, so this is your interest rate. We want to change this into a decimal, so divide by 100, we get 0.06. Compounded monthly. So monthly, there are 12 months in a year, so that means N is 12. So how many times the interest is applied to the amount of money. And a period of 3 years, this is your T. All right, so we have the formula A equals P, 1 plus R over N to the NT. We need to figure out that amount after 3 years. So we plug in the 50, 1 plus 0.06, that's the rate, over 12. That comes from being compounded monthly. And then NT is 12 times the number of years, which is 3. Okay, so basically you plug this into the calculator. So 50, parentheses, 1 plus 0.06 divided by 12 to the power 12 times 3. Make sure the 3 is multiplied up there, so maybe you need to use parentheses. 12 times 3, or just do 12 times 3 in your head. All right, there you go. You get 59.83. So $59.83. Make sure that I wrote things down. Yeah. All right, so after 3 years, that's how much money you have into the account. All right. So this formula, again, you can sort of apply and you can figure out the amount. Let me explain what's happening. Okay, so basically, this compounded interest. So you start with $50. So at time 0, you have $50. Okay? And then the bank goes into your account, and each month it applies the interest to it. So you have 1 month later, they're going to take that $50 and they're going to apply the interest, which is 0.066% per year. But because we're applying the interest over 12 months, you want to divide that by 12. So you're applying a 12 of the interest each year. Okay, so if you do this operation, so 50 times 0.06 times 12, so divide by 12, then you get 25 cents. Okay, so at the end of that first month, you earned 25 cents. So you add these together, so 50 plus 25, so you're going to have $50.25 into your account at the end of month 1. Okay, now the second month, right, you take that $50.25, you're going to apply that percent over 12, spread over 12 months, and you're going to figure out how much money you have at the end of the second month. So 50.25, we get 0.25 again, or 0.251. So 0.251. We're going to add those amounts together. So we have $50.50 rounding. So that's the end of the second month. So you go to the third month. You take that new amount, $50.50. You apply the interest to it. Right? And then you do that, and you're going to end up with a new interest, which you add. Okay? So you'd be doing these, because they're 3 years, you're going to be doing this every month for 36 months. But we don't need to go through all these calculations step by step, because this is where this formula does. So basically, for 36 months, 12 times 36, you take the amount that you have and you add the 0.06 over 12 to it, and you multiply by the 50, and then you do that 36 times. So this formula contains all these calculations in it. Alright, so you don't have to go like step by step, you can do it all at once. But it's nice to know what's happening. Basically, in practice, this is, you look at your bank account, this is what you're going to see. The initial 50, then $50.25, and next month is $50.50, and next month is going to be a little bit more, because that interest is calculated and added to your amount every month. Okay? And at the end of 36 months, this is what you end up with. Alright, let's look at the next problem. So we're investing $700 at 6%, so this is your P. Your R is 0.06 again. Compounded daily, there are 365 days in a year, and a period of 2 years, so T is 2. Okay? So the amount is the principal, 700, 1 plus 0.06 over 365, and then N times T, so 365 times 2. Alright, so plug that into the calculator. 700 parentheses 1 plus 0.06 divided by 12 to the power parentheses 365 times 2. Yep, that's not 12, that should be 365. There we go. $789.24. $789.20. Is it 24 cents? There we go. That's it. All right, let's look at the next one. $400 invested at 7% compounded continuously after a period of 3 years. So continuous, the formula changes. It's going to be A equals P e to the RT. So P is 400, R is 7% in decimal form, so 0.07, and T is 3 years. So we have 400 times e to the power 0.07 times 3. Let's go to the calculator and plug that in. 400 e to the power parentheses 0.07 times 3. All right, 493.47. 493.47. Okay, so continuous compounding is the one that gives you the most bang for your buck. All right, so the more often you compound the interest, the more it adds up at the end. All right, so let's look at effective rates of return. So the effective rate of interest, RE, of an investment earning an annual interest rate is given by this formulas right here. Okay, so if it's compounded n times a year, the effective rate of return is 1 plus r over n to the n minus 1, and continuous compounding is e to the r minus 1. So the effective rate of interest is basically if you're applying the interest just once in a year, you want to get the same amount as if you're applying it several times a year. So it gives you which rate of interest that you use if you were to just apply it in a lump once a year. Okay? All right, so let's look at finding the effective rate of interest for 6% compounded monthly. Okay, so R is 0.06 and n equals 12. So the effective rate is 1 plus 0.06 over 12 to the 12 minus 1. All right, plug it into the calculator. 1 plus 0.06 over 12 to the 12 minus 1, 0.0617. 0.0617. All right, so this is like 6.17%. Okay, so this is what this means. Okay, so let's say that I'm doing this 6% compounded monthly. All right? So for 1 year. All right, so let's say I have an amount of money. Let's say I start with like $100, and I'm going to put it in the bank for a year at 6% compounded monthly. Okay, so I'm going to get 100 times 1 plus 0.06 over 12 to the 12. All right, and then let's see how much I get. So 100. $106.17. All right, so that's the amount of money we end up at the end of the year. Okay, so what the effective rate of interest does is that if you apply this, if you try find the amount with principal times the rate with a time of 1 year, then the principal was $100, and I'm going to multiply it by 1 plus the rate, 1 plus 0.0617. Then I have 100 times 1.0617, which gives me 106.17. Okay, so we get the same thing. So basically the effective interest rate is what rate of interest would be equivalent to this one compounded monthly if you just compound the amount just once during the year. All right. Okay, so let's look at B. So we want to find the effective interest rate for 6% compounded continuously. So we use this formula now. So we have R equals 0.06 compounded continuously. So we have the effective rate of interest is e to the 0.06 minus 1. So we have e to the power 0.06 minus 1, which is 0.0618. 0.0618, which is 6.18%. Okay, so if we compare these two parts, so for compounded monthly, the overall percentage for the year of interest is 6.17. If I compound continuously, then it's going to be 6.18% a year. So you can see that compounding continuously will give you slightly more money at the end, right? If I applied this to that $100, then you end up with 100 times 1.0618, which is $106.18. So you get 1 cent more. It makes a difference if over the years, and if you have more money, then it makes a bit more a difference than that 1 cent. All right, let's look at present value. So the present value, P of $8 to be received after 2 years. If you compound it several times a year, then you have this formula, and if you're compounding continuously, then it's this formula. So basically these are just the initial formulas reversed, right? So here, this is like the amount t years later, and this is the amount at present, all right? Well, when you first invested. So if I solve for P, we get A divided by 1 plus R over N to the NT. And then if I write this as a negative exponent, we get A 1 plus R over N to the negative NT. Right, so basically you can see that we're solving for what should you have invested to get this amount t years later. Okay, and same for here. If I solve for P, I get A divided by E to the RT. Change this to a negative exponent, A e to the negative RT. So what should I have invested originally? That's what P is, to get this amount of money 2 years later. Okay, so that's what these formulas mean right here. Okay, so let's look at this example. Find the principal needed to obtain each amount. That is, find the present value. So I want to get $75 after 3 years at 8% compounded quarterly. Okay, so this is the amount that I want to get 3 years later, rate of 8%, so 0.08, quarterly compounding, and it goes 4. Okay, so I'm trying to find the principal, which is which amount should I put in the bank, all right, to get $75. 75, 1 plus 0.08 over 4 to the negative 4 times 3. All right, so let's plug that in. So 75, 1 plus 0.08 divided by 4 to the power, parentheses, negative 4 times 3. 59.14. 59.14. So you need to invest, put in the bank $59.14. So 4 years later, with that interest rate and that compounding style, you're going to get $75 at the end. All right, so it's working backwards. All right, let's look at B. I want to get $300, so this is your amount. 4 years later, T is 4. Interest is 3%, so 0.03. Compounded daily, so N is 365. All right, so the principal you should have invested is $300, parentheses, 1 plus 0.03 divided by 365 to the power negative 365 times 4. Go to our calculator. 400, no, it's 300. 1 plus 0.03 divided by 365 to the power, parentheses, negative 365 times 4. 266.08. 266.08. So that's the money you should have invested to get $300 after 3 years. All right, let's look at one with continuous compounding. So the amount I want to get is $800. The time is 2.5 years. Rate is 0.08. Okay, so this formula, we need this one. So the principal equals the amount, e to the negative 0.08 times 2.5. All right, let's plug it in. 800 e to the power, parentheses, negative 0.08 times 2.5 years. 654.98. So that's the amount you need to invest to get the $800 after 2.5 years. Alright, so let's look at the next example. Let's see which one is a better deal. So is it better to compound at 8% semi-annually or at 7.9% compounded daily? Okay, so we're going to use the initial formulas that we use. So the amount equals P1 plus R over N to the NT. So the amount is going to equal to principal 1 plus 0.08 over semi-annually means N is 2. 2 times, let's take the time to be 1 year. It doesn't matter if you take it 1 or 10, as long as you're comparing. We're doing the same for both. So let's just take the time to be 1 year. So the amount is going to be the principal times 1 plus 0.08 divided by 2. Oops. That didn't work out right. 1 plus 0.08 divided by 2 to the power 2. 1.0816. Alright, so with this compounding, you are going to multiply your initial investment by this factor. Okay? Now let's look at the second option. So I have the amount is the principal. 1 plus 7.9% would be 0.079. Daily, N is 365. To the power NT, so 365 times 1 year. Right, so let's do that. 1 plus 0.079 divided by 365 to the power 365, 1.082. So amount is the principal, 1.082. Let's carry the next decimal. 822. All right, so we compare these two numbers. We see that in this second case, this factor is bigger. So because we're multiplying by the same amount, you can say this is the better deal. All right, let's look at the next comparison. 9% compounded quarterly, where n is 4. So and again, look at over 1 year. So we have the principal 1 plus the interest 0.09 divided by 4 to the 4 times 1, compared with 9.25% compounded annually. So n is 1. So amount is the principal 1 plus 0.0925 over 1 to the power 1. Okay, so let's do this one first. And we don't need to do any calculations. 1.0925. Okay, so this gets multiplied by a factor of 1.0925. This one, we gotta plug it in. Okay, 1.09 divided by 4 to the 4 power. 1 plus 0.09 divided by 4 to the power 4. 1.0931. 1.0931. Let's see, this is bigger than that, so this is a better deal. You end up with more money at the end. Alright, let's look at these next couple of examples. So here we want to figure out what rate of interest compounded annually is required to double an investment in 6 years. Okay, so we're compounding annually, so n equals 1, t equals 6. All right, so we have the amount is equal to the principal 1 plus the rate over the time times nt, 6 times 1. All right, so we want this to double. So whatever the principal is, the amount needs to be twice the principal. So 2p equals p, 1 plus r to the 6. Divide both sides by p. So I get the equation 2 equals 1 plus r to the 6. All right, now we can do natural log of both sides. We have log of 2 equals 6. Oh no, that's not a good idea, because then my variable is going to be stuck inside the parentheses. So 2 equals 1 plus r to the 6. So we're going to raise both. We're going to take the 6th root. So to the power 1 over 6 and to the power of 1 over 6. This gives me to the power 1. So I have 2 to the 1 over 6 equals 1 plus r. So r is going to be 2 to the 1 over 6 minus 1. All right, so let's plug that in the calculator. 2 to the power 1 over 6 minus 1. 0.1225. Alright, so this means 12.25% annual interest. That's high interest. Alright, let's look at the next one. What rate of interest compounded annually, and is 1, is required to triple an investment in 10 years? So we have our principal, we want to triple it, so the amount needs to be 3p. 1 plus the rate over 1, 10 times 1. Divide both sides by p. So we have the equation 3 equals 1 plus r to the 10. Alright, so now we're going to do 1 over 10 to both sides for the exponent. 10 times 1 over 10 is 1. And we get 3 to the power 1 over 10 equals 1 plus r. So r equals 3 to the power 1 over 10 minus 1. All right, we do that with a calculator. 3 to the power 1 over 10 minus 1. 0.1161. Alright, so this is 11.61% interest. Alright, let's look at next example. How long does it take for an investment to triple in value if it's invested at 6% compounded monthly? So we want our principal, 1 plus 0.06, monthly means n is 12. And here I have nt, so 12 times t. And we want it to triple, so we want to end up with 3 times the original amount. So we're going to cancel this. We have 3 equals 1 plus 0.06 to the 12 to the 12t. Alright, so now my unknown is in the exponent. This is when I take the log of both sides. Right? So this 12t is going to go in front. So I have log of 3 equals 12t times log of 1 plus 0.06 divided by 12. Divide by 12 and divide by this. On both sides. So we get t equals log of 3 over 12 log of 1 plus 0.06 divided by 12. Alright, we're going to put that in the calculator. So log of 3 divided by 12 log of 1 plus 0.06 divided by 12, 18.4 years. 18.4 years. Alright, so approximately this is how long it will take for this to be tripled. Alright, part B, how long does it take for if the interest is compounded continuously? So same problem, we want to triple it. So for continuous interest, we have the principal e to the RT. So interest rate is 0.6 times the time, and we want the amount to triple, so 3p. Divide this, so we have 3 equals e to the 0.06t. Take the log of both sides, ln and ln. Here, log and e are the same base, so we cancel it out. And we have log of 3 equals 0.06t. Divide by both sides by 0.06. We have t is log of 3 divided by 0.06. And our calculator says log of 3 divided by 0.06, 18.31. So 18.3 years. Alright, so continuous will get you there slightly faster. Okay, let's look at some application problems now. Other application problems. Time required to reach a goal. So if Angela has $100 to invest at 2.5% per annum, compounded monthly, how long will it be before she has $175? If the compounded is continuous, how long would it be? So we have two parts here, compounded monthly and compounded continuously. So she wants $175. So we want to figure out how long. She starts with $100. So we have 1 plus r over n, so 0.025 divided by monthly, that's 12, and then 12 times time. Right, so we got to figure out the t. Okay, so we have 175 divided by 100 equals 1 plus 0.025 over 12. Let me actually do that, just so we write less. 1 plus 0.025 divided by 12. I don't like to round, that's the problem. Okay, so I'm gonna leave it like this. 1 plus 0.025 divided by 12 to the 12t. Alright, we're going to take the log of both sides. So the 12t comes in front. Alright, so we have log of 1.75 equals 12t log of 1 plus 0.025 divided by 12. Divide both sides by 12 and by the log. We get t equals log of 1.75 divided by 12 log of 1 plus 0.025 divided by 12. And plug it into the calculator. 75 divided by 12 log of 1 plus 0.025 divided by 12. 22.41. So 22.4 years. That's a low interest rate. Oh, this is a long time to get $75. Wow. All right, let's look at B. It's like, don't do it. Find a higher interest rate. So if compounded is continuous. Okay, so now we have to go. We want $175. We start with 100. Continuous means e to the RT. So 0.025 times the time. Divide by 100. Alright, so we have 175 over 100 is e to the 0.025t. Take the log of both sides. So log of this, log of that. This cancels because we have base e. We have log of 1.75 equals 0.025t. So t is going to be log of 1.75 divided by 0.025. We're going to figure that out. $22.4. So this is 22.4 years. Same amount of time. Doesn't make much difference if you compound monthly or continuously. So continuously compounding interest is the most popular way of doing things in practice, and you can see why. The calculations are easier because of that e. When you take log of both sides, it just cancels out. So it's a lot less messy. Alright, let's look at 8. John requires $3,000 in 6 months to pay off a loan that has no prepayment privileges. If he has the $3,000 now, how much of it should he save in an account paying 3% compounded monthly so that in 6 months he will have exactly $3,000? Okay, so this is like a one of those problems where we trying to figure out how much to put in. Okay, so he wants $3,000 at the end of 6 months. Okay, he already has $3,000, but he wants to spend some of it. So he wants to know how much to put into the account in order to get back to the $3,000 through interest. Okay, so he needs to know this amount. Okay, so there's 3%, so 1 plus 0.03 compounded monthly, which is 12, and then NT is going to be 12 times 6 months. 6 months is half a year, so it's going to be 12 times 1/2. Okay, So the amount is going to be $3,000 divided by 1 plus 0.03 over 12 to 12 times 1/2 is 6. Okay, so this is like the present value formula. So we have 3,000 divided by 1 plus, I forgot the interest rate, 0.03 divided by 12 to the power 6. 2955.39. $2,955.39. Okay, so he can spend about $44 out of that money. Most of it he has to put in the bank. All right. Let's look at the next example, comparing two alternatives. Suppose April has access to an investment that will pay 10% interest compounded continuously. Which is better? To be given the $1,000 now so that she can take advantage of this investment opportunity, or be given $1,325 after 3 years. Okay, so let's take April and use the continuous interest formula. So she's going to put $1,000 in the bank with 10%, so R is 0.10, and let's see how much she gets after 3 years. Okay, so put that in the calculator. 1,000 e to the power 0.1 times 3. $1,349.86. So that's how much money she would have after 3 years if she invested, but she would get $1,325 after 3 years, so this is a better deal. So take the $1,000 now and invest it herself. All right, let's look at example 10. Analyzing interest rates on a mortgage. Colleen and Bill have just purchased a house for $650,000 with the seller holding a second mortgage of $100,000. They promise to pay the seller $100,000 plus all accrued interest 5 years from now. If the seller offers them 3 interest options on the second mortgage, simple interest at 6% per year, 5.5% interest compounded monthly, or 5.25% interest compounded continuously, which option is best? That is, in which results in paying the least interest on the loan. Okay, so let's look at A. So the loan we're looking at the second mortgage, right? So the loan they're taking on the second mortgage is $100,000. So that's the amount. So we need, the amount is the principal of $100,000. Simple interest means you take the amount and you multiply by the interest and then times the time, which is 5 years. Okay, so that's the simple interest formula. Amount is principal times rate times time. All right, so let's do that. 100,000 times 0.06 times 5, $30,000. Alright, so that's how much they're paying in interest on that option. On option B, compounded monthly, we have $100,000, 1 plus 0.055 divided by 12. 12 times 5. All right. So 100,000, 1 plus 0.055 divided by 12 to the power 12 times 5. $131,570. .38. All right, so now this is the total amount, right? You go from 100,000 to 131,000. So the interest part is if you subtract these. Okay, so the interest is going to be 131,000 divided by 100,000. So it's the $31,570.38. All right, so far A is better. Okay. 5.25% interest compounded continuously. So the amount is going to be 100,000 e to the 0.0525 times the 5 years. Right, so 100,000 e to the power 0.0525 times 5. 130.1765. 17.65. Okay, so this is the total amount. The interest is going to be this minus the original 100,000, so it's $30,017.65. Alright, so the least interest that they would pay would be with the simple interest. So A is the deal that they should take. It's the best deal. Alright, there we go. Okay, that's it for the section.